Hey everyone, welcome to Data Smoothing Part 2, Lowess. So Lowess is a more advanced technique for smoothing the data, and it stands for locally weighted scatter plot smoothing. I think it's best explained whenever you see the scatter plot. So I'm just going to show the scatter plot of the daily case data from Texas. So the way Lowess works is that at every single point that you see here, what it will do is it will take a window of points. That means it does essentially a very similar thing as the moving average that we just covered. It looks at a window of points around the current point. But instead of taking the average, and that's what moving average did, we're going to fit a regression line through that point. So yes, at every point we'll fit just a simple linear regression line through that point, and it will only use the points around it. So fitting a single linear regression line through, like this whole series of data would not be very good, right? So we get some kind of line that would sort of get the trend, but it would just be a very bad linear regression line. So Lowess is a technique where you just fit lots and lots of linear regression lines and only consider the points right around the current point that you care about. So that's how you get an estimate for each of the points, and it'll look like a nice smooth curve through here. And one other thing that Lowess does is that it weights the points according to their distance from the current point. So say you're over here somewhere in mid-September, and what it does is the points, maybe your window size is something like 15 days on either end. So the points further away from the current date, if it's like September 15th or something, will get less weight than the other points. So that's where the weighted comes in. So locally just means look at the closest end points, and then you're going to weight those points by their distance from the current point. So that's what Lowess does. And there is in Python, it is found in the stats models package. So you cannot do this in pandas. There's no Lowess in pandas. So the stats models package provides this, and here's a link to it. So if you go here, you can read a little bit about what Lowess does. The main parameter here is I'll zoom here a little bit, is the frac parameter. So it's instead of giving it n like we did in pandas with the moving average for the number of points, you have to give the fraction of points for it to use. So it's going to be a number between 0 and 1. So this might need to be calculated. So if you want to get like 20 points, then you need to do like 20 divided by n, and I'll look at those nearest 20 points and fit a simple linear regression line through those 20 points. Okay, so you have to dig a little bit to find it. It's in some sub packages in stats models, and here's the actual function itself, Lowess. So you pass the 2 at the y, then x, and the main parameter here is frac. And what I've done here is I've just calculated the fraction of points. So I wanted to use 20 points. Well, I needed to do 20 divided by the length of the series, and that will give me the fraction to use here. And if I press Shift Tab, we'll see that, yes, so here's the fraction. It's set to 2/3, which is actually quite a large fraction of the points, so it will basically over smooth, in my opinion. So that's actually far too many points to consider for Lowess. A smaller range is going to be better. Okay, so y Lowess is just the smooth values. So let's go ahead and plot the smooth data through the actual. And now I'm just showing all of the data again. I'm not just looking at the last 200 days. And you can see it's quite smooth. And you can play around with this fraction to get a different number. And just to show you, if we use a larger number, say 80 points, we'll get a much smoother curve. And we might be missing out on some of the up and down over here. And you can see here at some points it'll be a little bit higher and lower. So let's just bring it down maybe to 40, see what that looks like. And that's probably fine. We can just stick with that for now. Okay, so that is the daily cases. Let's look at the cumulative. So when we look at the cumulative, we're just taking that Lowess and we're just summing it up and keeping track of it like that. And it appears to fit over the actual cumulative pretty nicely. Now, we're going to do one little thing here to correct for the, it's not going to lie exactly on top of the line. So we'll just do a little correction. This isn't 100% necessary, but just to show you the last actual value is 2.45 million. And the smooth value is a little bit less, 2.43 million. So they don't exactly align. And the reason you don't have to consider this is that when you build the model, what we'll do is that you can just consider the change. So if our model predicts the next day, if we're using this last smooth value, well, that's okay, because we'll just consider the difference between that and the actual, and our predicted value, and then add it to the actual, instead of just adding it to the smooth, because we know what the actual data is, and if our model is just predicting the very next daily cases, then we can just add it like that to get where it would actually be. Okay, so one thing we can do, this is just very simple. We can just find the difference between the actual and the smooth, or just find the fraction that it is above it. So we'll just divide the actual divided by the smooth, and that's what we just do here. And then we'll multiply it by the smooth. So we'll just kind of raise it up so that it now equals the same as the actual. Okay, so Lowess is actually the that's the discussion on Lowess, and it is the type of smoothing we will use on the data. It's a little bit more robust than the repeated moving average. It is a little bit more, it's definitely more computationally intense. So if you go back here, if you look at what's happening, it's fitting lots and lots of regression lines, and fitting a linear regression line is much more computationally intense than just taking the average, right? And there is a parameter in Lowess you could say it's called the delta parameter, which you can use to say, instead of, you don't have to look at every single point, right? Like, it's not like the regression line from one day to the next is going to change all that much. So what you can do is say, just look at points that are separated by some distance, and then just connect them with linear interpolation. So that's a way to actually save quite a lot of time. And you could see, just by doing every third or every fourth point, you would cut the regression line, or the number of regression lines used or calculated, by a third or by a fourth. So it can be a pretty big speed up. But it turns out it's not too bad to just leave it as the default and calculate regression lines every day. But that parameter is called, if you look over here, it's called delta. So you can certainly play around with that and use it if you don't want to, if you want to save some time. Okay, so that wraps it up for Lowess smoothing, and it is the type of smoothing that we are going to use right before we send the data to our model.